Welcome to the second installment of the MoleculeCrafter video tutorial. Here we'll be talking about viewing the file in ChimeraX. Now, there are two general types of files in the protein databank: structures that have been determined by X-ray diffraction and structures that have been determined by NMR. An X-ray determined structure will not have hydrogen atoms included in the file because this method cannot accurately determine their location. Since many of the bonds we will need to model are between hydrogen atoms and some other atom, we will need to add those hydrogen atoms back in. We can see here that the 1BNA structure I have chosen was determined by X-ray diffraction. This means it has no hydrogens. We will need to add hydrogens to the MMSIF file that we downloaded before we can extract the data from it. Note that if we had chosen a different file, such as this 139D, which, as you can see, was determined by NMR, it would already have hydrogens and we would not need to add them in. However, our structure is 1BNA and it does need hydrogens. What we do next is use the open source molecular visualization tool ChimeraX. What you want to do is select Open, choose the file that we previously downloaded. Now, Chimera allows you to change how you view your molecule. While this tube and slab shape is the default, I like changing the format so that I can see what happens to the number of atoms when I add hydrogens. So I'll go to Nucleotides, select Plane, go to Molecule Display, hide Cartoons, and then switch to a ball and stick model so I can see all the atoms. Now this was all just visual details and I haven't done anything else to alter the structure yet. But now I'm going to add hydrogens. To do that, I need to go to Tools, go to Structure Editing, and select Add Hydrogens. I want to make sure the method is steric only, and then I'll click OK. As you can see, all those white atoms that appeared on the structure are hydrogen. They have now been added to the MMSIF file and their coordinates can be extracted for use just as easily as the other atoms in the structure. So I'll want to save this, so I'll go to Home, I'll click Save. I'll need to put in a file name. I like keeping the 4-digit PDB code, but then adding something that lets me know this file has hydrogens. We want to make sure the file type is still an MMSIF, and then I just press Save. While we are in Chimera, this is the point where we should plan out what nucleic acid bases we want to model. So let's go to Molecule Display and change to nucleotide colors. As you can see, this DNA strand has 4 distinct bases and a backbone, so we need to model 5 unique substructures to be able to build the overall structure. This means we need to choose the most ideal version of each base to model. Deciding what is ideal is often a subjective process and can mean different things depending on your purpose. For this model, I'm looking for bases that are most nicely in plane. If we look at cytosine and guanine pairs, we can see that this top pair right here appears fairly twisted, while the ones below it, if we arrange our orientation just a little bit, we can see that these bottom two appear more in plane with each other. I will choose these two to be the ones that I model, as opposed to these two up here. If I hover my mouse over the base, I can see that this cytosine, marked DC, is on chain B and is strand sequence number 15. Its partner, this guanine over here, is on chain A and is sequence number 10 of that strand. I choose the adenine and thymine bases in the same way. For this structure, I've decided on choosing the adenine sequence number 17 on chain A and thymine number 8 on chain B. So this adenine right here, number 17, and its partner thymine, number 8, on chain A. Now, the backbone can be tricky. Choosing a backbone that is not ideal can have consequences when you build your structure. This may require you to try printing a couple of times before finding one that works as an ideal piece. I ended up choosing the sugar connected to thymine sequence number 7 on chain A. That would be this backbone piece right here. The main hint I can give to finding ideal backbones is to look at how they connect to the backbones on either side of them in the chain. For instance, does this connection point look to be oriented in the average manner for the structure? Now, because the backbones connect to other members of the chain, I will need to export the residues on either side of my chosen backbone as well. This means if I've chosen DT7 on chain A as my backbone, I'll need DT8 on chain A and DT6 on chain A as well. Now that I have all the residues I want to model, plus their chain and sequence numbers, I can move on to the next step, which is extracting the atomic coordinate data.